Every second, your senses are bombarded by a massive volume of raw physical data. Your brain discards almost all of it immediately. To be retained, information must survive a three-stage biological pipeline: encoding, storage, and retrieval. First, sensory input is encoded into a usable format, like a picture, sound, or meaning. Then, the brain maintains that data through storage and eventually locates it through retrieval. People often default to treating the system like a computer hard drive, a passive box where data sits quietly on a disk until you call upon it. In the late 19th century, psychologist William James challenged that assumption, proposing a dualistic theory of memory. James argued that memory operates within a strict dichotomy. Information is either transitory, meaning it is briefly perceived and lost, or it becomes permanent, staying in the memory forever. Mapping this architecture revealed the mind as a highly constrained processing engine, distinct from the static storage containers once envisioned by James. By 1965, cognitive scientists needed to move beyond theory and build a formal architecture to explain the specific mechanics of how data moves from temporary perception into permanent retention. This diagram shows the model published by Nancy Waugh and Donald Norman. It served as the birthplace for the formal concept of short-term memory. The first step in their schematic shows a stimulus successfully entering primary memory. Once inside, the data requires active effort to stay alive. The model identifies this mechanism as rehearsal, the mental repetition of information to keep it active. If you fail to rehearse the information, it drops out of the system entirely and is forgotten. However, with sustained rehearsal, the item successfully crosses the threshold into secondary memory, entering permanent storage. This model established that preventing data loss requires continuous mechanical effort. By isolating rehearsal as the key variable, researchers could begin testing the precise structural limits of that initial holding space. 3 years later, Richard Atkinson and Richard Shiffrin expanded this logic into the multi-store model, dividing the cognitive architecture into 3 distinct holding environments. They proposed that each store operates under its own strict independent characteristics for capacity, duration, and how it encodes data. The center block represents short-term memory, acting as the primary structural bottleneck for all incoming data. Psychologist George Miller quantified the capacity limit of this bottleneck with his magic number 7 ± 2. Miller theorized that an adult's short-term memory possesses roughly 7 open slots. Regardless of what the specific information is, the system can only handle between 5 and 9 individual items simultaneously. Cognitive science now viewed human processing as a rigid, linear pipeline trapped by a hard 7-slot capacity limit. The problem with this architecture is that it failed to explain how humans seamlessly handle complex, multi-layered tasks in reality. If the human mind is truly bound by a hard limit of 7 mental slots, processing the large volumes of data we encounter daily should crash the system. The human mind circumvents this bottleneck using a cognitive compression technique called chunking. Looking at this comparison, the unchunked data feed on the left presents 14 discrete items. This exceeds Miller's limit and guarantees memory failure. But by grouping those 14 distinct items into larger conceptual units, frozen foods, dairy, and bakery, the cognitive load bypasses the limit. You are now only occupying 3 structural slots. Chunking proved that short-term memory was functionally malleable, driving researchers to develop models that accounted for active data manipulation. In 1974, Alan Baddeley and Graham Hitch addressed this flaw. They took the single short-term memory box and fractured it into a network of distinct interconnected processing modules. This schematic details the 1974 working memory model, a system of independent components designed to process different data types simultaneously. At the center of the diagram is the central executive, acting as the driver and manager for the entire network. The central executive continuously allocates data to the separate subsystems while also directly processing high-level cognitive tasks like mental arithmetic and problem-solving. One of the primary subsystems it delegates to is the Visual Spatial Sketchpad, often initialized as VSS. The sketchpad serves as the inner eye. It operates as a fully independent processor dedicated entirely to analyzing visual form and managing spatial navigation. By separating the central executive's management duties from the sketchpad's visual storage, the brain avoids catastrophic interference. You can calculate a math problem in your head and navigate through a physical room at the exact same time. The central executive routes spoken and written material to a separate acoustic module, the phonological loop. The first mechanism is the phonological store, acting as an inner ear linked to speech perception. The phonological store is highly volatile. It holds speech-based data for a maximum of 1 to 2 seconds before the information naturally decays. To prevent that immediate loss, the system uses the articulatory control process. This is your inner voice, which actively rehearses the verbal information and feeds it back into the store. This continuous subvocal loop is the exact mechanical reason you can hold a phone number in your head just long enough to dial it. These diagrams map onto the physical brain. Acoustic processing of the phonological loop routes through language centers in the left hemisphere. Conversely, the visuospatial sketchpad routes visual and spatial data primarily to the right hemisphere. This final infographic illustrates how the central executive gathers these independent physical processing streams to construct reality. The arrows flowing from the inner eye and inner voice show continuous, parallel data buffering directly into the central workspace. The evidence suggests that memory serves as a live, demanding workspace. Human cognition is the result of a precise synchronization between these limited subsystems. It is an active process where a central executive routes and buffers distinct data streams to generate the continuous experience of conscious awareness.